talked about coherent states. Okay, so we had psi 1, psi 2. Oh, so okay, so A psi is equal to psi psi. These are coherent states, and psi is defined as e to the zeta psi A dagger acting on the vacuum. Okay, and here zeta is 1 for bosons and -1 for fermions. Okay, and then we saw that the overlap between two such coherent states is given by e to the psi 1 bar psi 2, and finally we also saw that one can define the identity matrix in this space in the following manner: an integral d psi bar psi e to the minus psi squared, where we interpret this absolute value as the product of psi bar and psi, which in the case of Grassmann variables is not exactly absolute value. Psi, outer product of psi and psi, and the only comment to make here is there are two comments. One of them is that this guy here includes factor of 1 over pi for bosons. Okay, so for example, there is normalization. This guy can be sum over j psi j squared, in the sense that we might think of these psi's as some sort of vector in short notation. And the final thing is that this here factor is there to compensate because the coherent state basis is an overcomplete basis. Okay? So, good. And then what we were after, what were we after? We were trying to compute the partition function. So the partition function, by the way, at which stage can't you see? Let me see. Okay, that's about it. So next time maybe it's better you sit here, then you'll see better. No?
I can't see fine.
But if I write here, you can't see, right?
No.
Okay.
אתה רואה שיש שם נקודה כזאת? כזה ממש קטנה קצת שמאל? אחת למעלה? זאתי. That would
So yeah, so that's exactly what I meant. So if you move to here, there will. Anyways, never mind. Let's not get into a discussion about that. So the partition function z is defined as the trace, right, of e to the minus beta h. H is this huge matrix. It's like a many-body matrix. And to compute the partition function, we want to compute this trace. This is by definition a sum over whatever complete basis you want, n. n is a complete basis, okay? E to the minus beta h n, and we can convert this into an integral over r over complete basis. And then we find the following result: d psi bar psi e to the minus psi squared. And then we have something that looks like this. Okay, all this is just a reminder of what we did last time.
Whoa.
Okay? And this factor of zeta comes from the fact that if these are fermions, then these coherent states are defined using Grassmann numbers. And when you commute, them, in order to get rid of this sum over n, you collect this minus sign. And back in the last class, I told you that there was something I wasn't certain about, but I checked. This always works, and if anyone's interested, we can discuss that later. Now, the next step we did was we took this factor e to the minus beta h, this operator, and we wrote it as a product of many small increments. So e to the minus delta h to the power of n, where, of course, delta is beta over n, okay? And delta is assumed to be small. And to get the path integral, essentially, we will take delta to 0. Okay? And the calculation that we're going to do is only correct up to linear order in delta. We will see that in a moment. Then I'm rewriting this thing here, so I get an integral d psi bar psi e to the minus psi squared zeta psi. Then I have e to the minus delta h, e to the minus delta h, and so on and so forth until the last one, e to the minus delta h, and then I have psi. Okay, and now what I'm going to do is I'm going to inject this identity matrix in between at n minus 1 locations. So for example, here I'm going to stick an integral d bar psi 1 e to the minus psi 1 squared psi 1 psi 1. Okay? And in between these two guys, I'm going to put, d psi bar 2 psi 2 e to the minus psi 2 squared, okay, like this. And then in the last one here, I'm going to put integral d psi n minus 1 bar psi n minus 1 e to the minus psi n minus 1 squared psi n minus 1 psi n minus 1. Okay? Any questions up to this point? This is basically where we stopped last time. And so what did I want to say here? So I just wanted to comment again. Yeah, okay. So what we want to do now is we want to apply this H on these coherent states. And the point is that we assume that H is what we call normal order. It means that all the A's, if you like, are on the right side, and all the A daggers are on the left. So the A daggers can act left, the A's can act right. So if H is something A dagger A is some function of these operators, then we want to say something like psi j minus 1 H A dagger A psi j is equal to H of psi j minus 1 bar psi j, like this, without the operator. This is now functional of these fields. Okay? Now, another comment that I wanted to make. Okay. Now, in principle, what we're going to do is we're just going to substitute this H here in the exponent with, with this functional. But you should note, and I mentioned this last time, that we can't do this. This is not exact. This is only up to linear order in delta. You could imagine, if you like, that we expand each one of these exponents into a series, and then we throw everything of order delta squared, and then this equation applies, and then we re-exponentiate. But of course, if you want to look at higher orders in delta, then you could imagine, for example, that you have like h squared, and h squared, if h is normal ordered, h squared is not normal ordered, right? So we can't use that trick anymore. Okay? That's important. Why am I saying that that's important? Why am I emphasizing this? Because if this weren't the case, then we could have done, we could have just computed this expectation value. So the whole process of separating into small increments and obtaining this path integral comes exactly from this. This is the origin of this. It's not that simple. Okay? Now, so now I can summarize what we have. After I'm going to use this equation quite often, right? Everywhere here, and I'm going to use this equation. Okay, under the assumption that I've just explained. So this is not exactly, this is approximately, I'm writing now. An integral, and now I have pi j is equal to 1 to n d psi bar j psi j e to the minus sum over j is equal to 1 to n. Then I have psi j squared plus psi j minus 1 psi j bar minus delta h of psi bar j minus 1 psi j, and then I close the thing. And here I made an assumption, and the assumption is that psi 0, what I define as psi 0, is zeta times psi n, okay, and which is zeta times psi, if you like, and psi 0 bar is equal to zeta psi bar n, which is essentially zeta psi bar. What do I mean by that? So here originally we had one psi which was didn't have any subindex. So now I'm going to denote this guy here is zeta psi n, if you like, and this guy is psi n. Sorry, psi n. Okay, so that's all I'm saying. Okay, now we're almost done. Right? Now we're almost done. because all I really need to do is rearrange these guys. Okay, I'm going to take a delta outside. Okay, outside. So I'm going to get that this, and by the way, when I wrote this approximately, this is plus O of delta squared. Okay, this is what I neglected. So this guy is equal to an integral. So this is Z now. Z is approximately pi j is equal to 1 to n d psi j bar psi j. And now I have e to the minus sum j is equal to 1 to n delta. Then let's see what I have here. I have, this is a mistake, of course. The minus sign should have been inside the brackets. Okay? In particular, this term is positive. This term is negative because it's this correction factor of the over-completeness of the basis. And this guy also comes negative because it's e to the minus beta h. Okay? So that's just a silly mistake. Okay? So now what I have here is psi j bar minus 1. So I have psi bar j minus 1 minus psi j bar. No, the other way around. Sorry. Psi j bar minus psi j minus 1 bar over delta times psi j. Yeah, I think I'm going to pay for this. Okay, we'll see later. Maybe I made a mistake here somewhere. And then plus h of psi bar j minus 1 psi j. Okay? And now the last step to obtain the path integral under this condition. I'm not writing it again. Now the last step I need to get the path integral is just to take n to infinity. And then when we take n to infinity, which is like taking delta to 0, we get our path integral d psi bar psi. Okay, this now becomes the measure of the integral, so it's an infinite product of these guys. And then this thing, so we get e to the minus integral from 0 to beta d tau psi bar times psi minus h plus h of psi bar and psi. Okay? And I think I made some sort of mistake with the signs, which I'll have to...
What is tau?
Tau, I'll explain in a moment what tau is. Tau is a mysterious entity emerging. Yeah, I made some sort of mistake. Let me see. Hold on one moment. I think I made a mistake in passing from here to there. Let me think about it. It's just that this time derivative is supposed to be the other way around. And I don't see... So I could take this...
Looks fine.
Okay, never mind. Let's not dwell on this too much.
The sign of h is the minus. Right?
No, it's getting a minus outside.
Yeah. minus outside. So yeah, and the condition is that psi of 0 again. Psi of tau equal to 0 is equal to zeta psi of beta of tau equal to beta. I'll explain in a moment. And psi bar of tau equal to 0 is equal to zeta psi bar of tau equal to beta. And to your question, what is tau? So remember that what we basically did here is a Riemann sum. So we define a tau j as equal to j times delta. Okay, so that gives us a time unit. And then we have an integral. This is the difference between points in this Riemann sum. We take delta to 0, this becomes an integral. Okay, and as you know, as you can see, when j is equal to n, it's beta. When j is equal to 1, it's essentially like 0. Take delta to 0. Okay. And I'll check it later, but don't be angry at me. But it's supposed to, at least in the books, it's all written like this. I don't know where I made a mistake. I'll check later, maybe. I think it's a matter of convention. I don't think it's really important, the sign of this term. This term has less importance regarding the sign. Okay? But now we have found a path integral way of computing this partition function. Okay? So instead of needing to deal with some huge matrix, instead we have a path integral over different configurations of the fields. Okay, and the configurations of the fields are weighted by these two terms. One of them is the Hamiltonian, the energy, which we expect, and the second one is this term, which we will discuss now in a little bit length. The second comment is that you can see that we have an emergent dimension. Okay, so tau looks exactly like imaginary time, which is not surprising. Okay, it's not surprising that it's imaginary time because you see there is an equivalence between e to the minus ith as an evolution operator and e to the minus beta h, which is what we just computed, under the assumption that beta is equal to it. So, if you like, this is like this dimension. You could think of it as some sort of analytic continuation of real-time action, okay, into the complex plane, and then this integral is written along the imaginary axis. So that's one comment. But another comment is that, I don't know how much path integral formalism you studied. I know that some of you did, some of you didn't, but I've already mentioned this last class. A path integral gives us the overlap, the probability of a certain overlap. Now here we have a many-body version of that, and the probability is basically the probability of the state starting at some coherent state, and then evolving whatever, and then going back to itself or going back to minus itself, and then we sum over all possible such field configurations. Okay. Okay. So and now this. So you could imagine that basically your the price that you pay from going, starting with an Hamiltonian, which depends, say, on space, when we go to the action formalism is that we have this emergent dimension, and basically all the particles, in addition to, let's say this is space, and this is imaginary time. So in addition to depending on space, particles also depend on imaginary time, and it's just another dimension. It's of course a mathematical trick, but this is our way of capturing quantum fluctuations, and maybe let me comment about that a little bit. So let me see. So I want to remind you that any place. Okay, so let's make a few comments. Any questions first? Yes.
What's the capital D stuff?
Capital D. So this is like some mathematical object called measure, because you have to remember that here we are making a product. There's a product, a discrete product of a finite number of integrals. Okay, so we're doing some Gaussian integral. It doesn't have to be Gaussian, some integrals. Okay, but when we take n to infinity, this becomes an infinite number of such integrals, and then it's a different mathematical entity. The only way I understand it, the only way I can make sense of it, is when I need to compute something, I make it finite, I compute it, and then I take n to infinity at the end. Okay, so I make it into a discrete product of such, and that's actually how we compute also path integrals.
So this is basically like some formalism.
Yes, it's a formal definition of the n going to infinity limit of this product. Okay, so a few comments. So again, I mentioned this a few times, but let me emphasize it again. So the first comment is that when I write psi bar of tau, psi of tau, this guy very well might contain spatial integration, spin, orbits. Okay, so what I actually mean is that these can be vectors in many, many different spaces. So it could be something like d dx sum over sigma psi bar sigma of tau and x psi of tau and x. Okay, so this is a shorthand notation for all these integrals which I have hidden under the rug. Okay, the second comment I want to make, notice that if we assume that the fields are independent on tau, we go back to classical statistical mechanics. Okay, so if I were to assume that the fields don't depend on tau, this term disappears. Okay, and this integral just becomes beta, and then all we have is just e to the minus and h. H is like some energy functional of the configurations of the fields. So whatever your fields are, they will be weighted by this h, and this will give you the partition function. So what this gives you, why am I emphasizing this. It tells you that tau dependence is where the quantum essence lies. Okay? It all comes from there. Okay, so without tau dependence, it's in principle a classical problem. Second comment is I want to make a comment about this term here, this psi bar d tau psi. We can associate the psi bar d tau psi term as with the commutation relations of a dagger and A. Okay? So remember that these psi's are eigenvalues, or these psi's are functions which are basically eigenvalues of coherent states of A. Okay? And a psi bar is the same for a dagger. Okay, and the fact that this term appears here is actually signaling to us that there is some non-trivial commutation relation. So when you have two fields that are that in the quantum mechanical, in the Hamiltonian formalism are not commuting, then in the quantum field theory version, they will be coupled in this way. Okay? So that's an important comment. We can see this in different ways. I can maybe any questions about that, or this is fine. Yeah, I'll skip because this shorter course this year. Any questions? No, nothing. Okay. So if not, now let's see how to compute things with such an integral. What can we do with this? Okay? Okay, so Matsubara frequencies. Okay, so as usual, it's going to be convenient to transform to Fourier space, and also in time we want to do this. So it's very simple what we do. So we write psi of tau as a sum over omega n e to the minus omega n tau psi n. Okay, this is the Fourier transform. And the equivalent is that psi over n is 1 over beta, 0 to beta, d tau e to the I omega n tau, psi tau. And the only reason this whole thing is worth noting, because it's quite trivial, is that remember that these fields live on the circumference of some cylinder. Yes. So in order to respect the boundary conditions, so naively you would say, okay, then omega n needs to be 2 pi n, and this is 2 pi over beta times n. And this is indeed the case for bosons. But for fermions, remember that they collect this extra minus sign, and therefore they behave weirdly. You need this fermions. Okay, so now let's get a little bit of let's get used to this. Example. So let's look at free fermions. Free fermions / bosons. Okay? Then H 0, which is the free part of psi bar and psi, is going to be some integral d dx and then we have something like let me write something like epsilon of minus I nabla epsilon of minus I nabla psi of x. Okay, so this is some generic Hamiltonian. Okay, and for now let's assume that this is diagonal. I'm not going to get into too much sophisticated things. Therefore, the action. Oh, I forgot to mention. By the way, this guy here is the action, right? Sorry, this whole thing is the action. Integral 0 to beta d tau psi bar d tau psi plus h of psi bar and psi. Sorry, I forgot to mention. This is what we call action. And indeed, if you transform from a imaginary time to real time, this is exactly the action. Okay, so this is if anyone ever studied field theory, then this is the action in Euclidean time. Okay, so if this is the Hamiltonian, then S naught is equal to an integral 0 to beta d tau, an integral d dx, and then we have psi bar d tau. Okay, maybe let me write it like this: x and tau d tau plus epsilon of minus I grad psi of x and tau. Okay? Now we perform the Fourier transformation. Transform to Fourier space, and we get S0 is equal to beta sum over omega n and k minus I omega n plus epsilon of k psi bar of k and omega psi of k and omega.
What is the difference? Why is this a fancier or is it the same?
What? It's just this is in Fourier space and that's in real space.
אוקיי.
So now, basically what I did is this is here, this is like a matrix, and this is like a matrix in a Gaussian integral, and here in this basis it's not diagonalized, and the Fourier transformation diagonalized the matrix. Okay? And that implies that z, okay, I can compute it immediately. This is the integral d psi bar psi e to the minus s of psi bar psi, in this case s0. So this just becomes sum over all product of these n and k's, n k, beta minus I omega m plus epsilon of k, and this one becomes 1 over beta minus I omega n plus epsilon of k. Okay? And this is for fermions, and this is for bosons. Okay, then we can conclude that Z is equal to the determinant of a diagonal matrix, which I will call beta minus I omega hat plus H hat to the power of this is zeta. Okay, and we can use this to compute the free energy. So say you want to look at the free energy, the free energy of free particles. Okay, that's given by F is minus log of Z divided by beta, and then the product becomes a sum, so we get minus zeta over beta sum over this n and k ln of, I'm looking at this, so it's minus I omega n plus epsilon of k. That's it. Okay?
Why didn't we start with the grand canonical partition function?
Good question. Good question. This is the grand canonical ensemble. I assume that epsilon of minus I delta is some h of minus I delta minus mu. Okay, so I always have a chemical potential to fix the density.
Yeah, but it didn't mean that here we should have psi and not f or g, however you want to call it.
Again?
We should have the grand canonical potential, not the Helmholtz energy.
This is not the Helmholtz energy, this is the free energy. The free energy is the relevant functional in the grand canonical ensemble. Potential. Okay? Okay, so what this expression shows us is that, and this is a common thread in these kinds of calculations, is that if we want to make any sense of this kind of field theory, we need to know how to perform what we call Matsubara sums. Okay, so we need a trick to compute the sum over these frequencies n. Now, what's different compared to k, hold on one moment, is that k, we often think about it as a continuous variable. Okay, it's momentum, say we have a large system, a large system compared to, say, the interatomic distance in the material or whatever. So we'll think about it as continuous. But n here is more tricky because depending on the temperature, it can be discrete in a way that we cannot neglect the... So we need a way to compute these sums. Yes?
אז כל אני באת שם מינוס, בין הלם זה אחד חלקי ביתה, בין מינוס בין זה חלקי ביתה. כאילו השארת שם מינוס להבין אותה.
Let's see. So...
זה נשמע הגיוני שחסר שם מינוס, כן, צריך את פלוס.
Maybe. Okay.
ואיך הגעת מהדטרמיננטה כאילו ל...
Okay. So first of all, I didn't explain exactly what these are. When I write omega hat, what I mean is a matrix that along the space of omega, it has the vector omega and its diagonal. And along all other spaces, it's just identity matrix. So it depends only on omega. Okay, and it's like a diagonal matrix. This guy is the Hamiltonian. So how do you compute the determinant? One very convenient way is to diagonalize this matrix and then take the product of the eigenvalues.
Wow.
And this is exactly what you see here. This is the product of these eigenvalues, and that's why I denoted it as a determinant to begin with.
Oh, alright.
It's because it's just a Gaussian integral, right?
Yes. Yeah, and remember that in the previous lecture, we saw that Gaussian integrals give us this determinant. Okay.
What letters are there after the equal sign?
This?
Yeah.
Zeta,
Okay.
beta,
What is it?
lan.
Okay.
Sigma.
This is sigma,
This is
n
fine.
and k.
This is fine now.
Maybe we should take a break.
If you want.
Yeah, let's take, okay. So in the next lecture, what I'll discuss is how to perform these kind of integrals. We will use this technique to compute the free energy, which will be useful for us in the future. And it's useful in general to know the expression for the free energy of free particles or quasi-particles. And then after we'll be done with that, maybe a few more comments. And then we'll move finally to do some real physics. And we're going to discuss the weakly interacting Bose gas. So the Bose gas is the segue to the superconductor. It's like we will first understand the process, the phenomena of condensation, superfluidity, flowing without friction, all these ideas, symmetry breaking, and then we will go to superconductor. Okay?
זה העיסוק שלנו.
Okay, so we want to compute a מצובר הסם. Okay, and we will get back to this specific sum. Okay, but for now, let us generalize it. So we want to compute מצובר הסams. We're talking about something of this form. How do we compute this? So the way we're going to do this is we're going to notice that the function g of z is equal to zeta beta divided by e to the beta z minus zeta has poles at omega n. Okay? So this function has poles at omega n. What does this imply? It implies that using Cauchy theorem, okay, imagine that hz, that h is a function, when I analytically continue it, it is properly analytic, or at least it has only some well-defined poles, okay? And then I make a contour, which I'll show you in a moment, such that this sum over n, h of omega n, is equal to, by Cauchy theorem, 1 over 2 pi I, the closed integral dz, g of z, h of z. Okay? So, and this contour, I'm going to draw it like this. Like a cucumber contour. And the idea is that, imagine that this is the imaginary of z, and this is real of z, okay? Such that the real of z is like t, and this is like tau. What am I talking about? No. This is like this I omega, I omega. Yeah, so the imaginary is omega, okay? The imaginary part is this omega, such that the poles are like this. For bosons, okay? And for fermions, they're like shifted by half. So for fermions, they do not hit 0. For bosons, they hit 0. Okay? And the contour that we're going to have is a contour that goes like this. Okay, all the way to infinity. And then closes somehow, comes back. Sorry for the squeaking. Okay, so this is the contour we're going to do. And then it might be that for whatever reason, there are some poles. Okay, let's do it like this. That there are some poles of h of z. So I'm not saying that h of z can't have poles, but we cannot collect them. They need to be somewhere out. Okay? And then this equation is correct. So now we're going to use this equation to compute the sum. So how do we do that? We're going to deform the contour. Okay? So as long as we don't cross any poles, then we can deform the contour. By the way, this guy has poles at the Matsubara frequencies. This you can check by yourself. So no one doubted me, but that can be shown. So what we're going to do is we're going to deform the contour. Deform the contour. You have a question?
Is it H or LAN or
H.
which
H
is?
is
No. So what we're talking about now? Okay, again. So just to put you into speed, to bring you up to speed. Sorry. What we want to do. So we saw, for example, that the free energy is a sum over these ends. So this motivates us to understand how to compute such what we call Matsubara sums.
So you said everything that is in the sum, you call this H?
Good. So I'm saying that when dealing with these kind of field theories, it's very common that in the end you need to compute some sort of sum like this. Okay? What we're talking about is we have a system at equilibrium. By the way, I forgot to mention this. All this formalism is correct for systems at thermal equilibrium. Right? We're computing a partition function e to the minus beta h. We're assuming the system is at thermal equilibrium and we want to compute all sorts of quantities. Turns out that to do that, you often need to compute such sums. So I'm just explaining how to perform such a sum. So this is a specific example.
H is a general.
This is a generic,
Okay.
yes, generic expression. And now I'm saying instead of, oh sorry, this is an I, it should be an I here. Instead of computing it this way, let's do an integral in the complex plane. Okay? And then what we do, okay, so we have this structure, we have this guy here and this guy here. We have these guys, okay? And we have our contour. Now what we're going to do is we're going to take this contour and kind of inflate it. So imagine that the contour kind of becomes like okay. 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 Yes. That's like this. Okay. Okay, so I've basically inflated this to infinity. And when I do this pictorially, what you can see is that now we can do this integral by virtue of the residue theorem. So instead of doing a sum over an infinite number of Matsubara frequencies, we convert the sum into a finite sum over a finite number of poles that this function h might have. This is, if you like, the advantage. So the idea will be to say that this guy this guy is equal to basically this guy. Okay, now this is an assumption, of course, that nothing bad happens in the middle, and that I can take this contour to infinity, and infinity it vanishes. All this depends on the properties of H, and you might need to worry about that. I'm not worrying about that now. I don't care, but if you do a calculation, you need to make sure that everything is fine. But if everything is fine, then we can do this. And then we've significantly simplified this integral. This sum, sorry. We've significantly simplified the sum because now we can perform it as a very small sum over residues. So what we obtain, let me summarize, is that h of I omega n is equal to the residues of h of z times g of z at z is equal to, let's call them epsilon j. Okay, let's say there's a sum over j. Okay, and these are these guys. Say this is like epsilon 1, epsilon 2. These are the poles of h. So poles of h of z. So let's see an example. Example. So this is basically the final result. Okay, this is basically what we really want to do. Okay, that's the idea. All the rest is just hand waving. So let's see an example. So we're going to do two examples, okay? One of them is the Green's function, and the second one is going to be this free energy. But let's start from the Green's function. So let's say h of I omega n is equal to 1 over beta sum over n 1 over minus I omega n plus x. Okay? And this could be a Green's function of some fermionic or bosonic mode. Okay?
Green function of what?
Of some bosonic or fermionic mode. So imagine that you have psi bar minus I omega n plus x, psi as your action, sum over whatever, okay? Then here, what sits here is basically the inverse Green's function. This is something you know or not really.
I remember something about it, but not particularly.
So maybe a good way of thinking about it is that if you take a functional derivative with respect to psi bar, you will get a differential equation for. Imagine that your action. Let's assume for a moment that your action is an integral d dx d tau, okay, or dt, even something like a psi bar d tau plus, I don't know, Laplacian over 2m minus mu psi. Okay, let's just assume for a moment that this is your thing. Okay, and you take a functional derivative delta s over delta psi bar. This would be, and you equate this to 0. This is what we call the saddle point of the action. The saddle point of the action is in the semi-classical limit. That's where you get most of the contribution to this field integral. Exactly for the reasons we've discussed before, because each one of them is like, you could think about it in two ways. Either you have e to the minus s, and you're integrating over this guy, so the minimum of s is where the integral contributes the most. Okay? Another way is if you have a complex integral, like you're doing a real-time quantum mechanics, then each one contributes a phase, and in the limit where in the limit where you take h bar to 0, which is the semi-classical limit, then it turns out that the locations where the phase, it's called caustics. It's like caustics, where you have the phase changes very, very slowly, which are like minimum points, contribute a lot to the, you have a instructive interference, because everyone kind of, the change of the phase with whatever parameter you're looking at kind of slows down, and then all the phases accumulate and they don't cancel each other. So in both cases, this part, and if you look at this thing, what you'll find is that this guy looks like dt plus Laplacian over 2m minus mu, okay, times psi is equal to 0. This looks like a differential equation of the kind I teach in my Mathematics 3 course, right? This is the operator, L, okay? And this is the function, psi, that I'm searching for. The inverse of this operator is what we call a Green's function. If this is if you have a force field, then the Green's function is used to find the inhomogeneous part of psi, for example. So what this tells you that whatever sits in the Gaussian part of the integral, of the field integral, okay, is related to the operator that will give you the differential equation of the saddle point solution, but also this is the inverse Green's function. So that's why people call this a Green's function. Now, if you Fourier transform, as I also teach in my course, if you Fourier transform the Green's function, you convert this complicated differential equation into a simple algebraic equation, which is just 1 over this. Okay? So that's why people call this a Green's function. Okay, that's why I call it a Green's function. And this is very common in like fermionic and bosonic field theories. You might find yourself computing these guys. Okay? So according to what we have over there, okay, we want to have a residue, okay? So you see this guy, I want to call, so I want to say that h of z is 1 over beta sum over n, h of z, yeah, what did I want to say? Sorry, this is a sum over n, okay? So h of z is 1 over minus z plus x. Okay, so this means that we have a pole at z, at x. The pole is at x. It's like the simplest possible thing. So therefore, I find that by the way, this is not h. This is a sum over h. Again. Okay, so the sum is going to be equal to basically the residue at x. So I find a 1 over beta, probably with a minus sign, g of x, which in our case gives minus zeta e to the beta zeta minus zeta. Right? Which indeed, okay, so the minus here, by the way, comes from the fact that this is not z minus x, but x minus z. Okay? And yeah, and this we get, and you know what this is, right? This is what we have here is basically n Fermi Dirac of x for fermions, and for bosons we have minus n Bose of x for bosons. And I'm sorry about the minus signs, I'm not very careful. It might be the other way around, but minus is not a big deal, especially in field theory. Okay? So what this shows you is that the sum over the Green's function, okay, gives you the distribution functions of bosons and fermions respectively. Bose-Einstein. Maybe let's give Einstein some respect. Okay? Okay, second example. Now let's do this guy. So in this case, h of z is minus 1. Oh, we said it's without the minus. You guys corrected me. It's 1 over beta, sum over k, ln of let's write epsilon of k minus z. Okay, this is what we have. So this is a bit different. So this implies that f is zeta over 2 pi I beta. The closed integral dz, okay, sum over k, ln of epsilon of k minus z, okay, times g of z, okay. Now this is a bit different from what we had before, because the log, right, if I look at ln z, right, ln z is going to have a branch cut here. It's not a pole anymore, it's a branch cut. Okay? Now in this case it's epsilon k minus z. So the branch cut looks like this. At least this is the most natural branch cut to choose. It looks like this. Here we have the point epsilon of k. Okay, and the branch cut goes along this line. So what that implies is that when I inflate my contour, I cannot cross this branch cut. Okay, non-analytic. Here I have my Matsubara poles. Okay, so what I'm going to do is I'm going to have a contour that goes like this, and goes all the way around and comes back. And it's going to be like, you know, a little bit above and a little bit below this branch cut. And then what do we have? So we have so you could imagine that this is an integral from infinity to epsilon of k. And this is an integral from epsilon of k to infinity. Okay? So I can write them both as zeta over 2 pi I beta, an integral from epsilon k to infinity, dz sum over k. Now I'm opening the bracket and I'm writing ln of epsilon of k minus z plus minus ln of epsilon of k minus z plus minus. And all this is multiplied by g of z. The minus sign comes because one time I'm going in this direction, one time I'm going in that direction. Okay? Now I'm going to do a dirty trick. And you have to agree with me that if I were to inflate this, like if instead of turning at epsilon of k, I would turn here, it would change nothing in the integral. Because here, there is no jump of I pi between them. Right? So they cancel each other. Only near the branch cut it contributes. So at the same price, I could just write here minus infinity. Should be the same result.
Except, what if there is a pole at 0?
That's true. Yeah, that's true. You're asking for bosons, basically. What happens with bosons? Yeah, I'll have to get back to you on that. I tend to be... Let's not worry about it now and worry about it later. What would be... So we would have an additional contribution from a pole at 0. We might need to subtract that to get the. But I think that's controlled. That's that I can control that. It just means that in addition to the integral, I'm going to get one additional contribution from this guy, which will give me the pole at 0.
But can
but at 0, I think they cancel. They cancel each other. Actually, it doesn't matter. This and this. These two will cancel each other.
Can you give some?
So let me just answer the. You can think about these as like two integrals. Hold on. Let me confirm. Okay, I'll have to think about that if that introduces anything. What's the question?
Can you give some intuition? What do the poles represent in statistical mechanics?
This is just a mathematical trick to compute the free energy. Okay, there is no the poles. In this case, the poles are the dispersion of the quasiparticles. By the way, it's not a pole; it's a branch cut.
No,
This is some continuum of excitation.
I mean, on this axis.
What?
This axis.
This axis, the Matsubara frequencies. Matsubara frequencies are, there I don't think I can give any physical intuition. It's just a mathematical trick to compute these integrals. Okay, so now, okay, hold on. So we remember, okay, so now, I think we integrate by parts. Okay, so we're going to treat these as, let's call this, U, and this, let's call it V tag. So we're going to switch to V and U tag. Okay, and we're doing the integral with the integration by parts with respect to Z. So we get minus zeta over beta, sum over k, 1 over 2 pi I, the integral from minus infinity to infinity, dz ln of 1 minus zeta e to the minus beta z. This is basically v. Okay, this is v. And then U tag is just going to be 1 over epsilon of k minus z plus minus 1 over epsilon of k minus z minus. Now let me think about this. Oh, there's an additional minus sign from here. Okay. From these derivatives. Now let me see what I get here. Here I get 1 over beta. That's another minus sign. Yeah, I think there are 2 minus signs. Maybe. Yeah, I don't know about the minuses. Yeah. It's a mess. I know. And these guys, what they give me is because one of them is a little bit above and one of them is a little bit below, then they just add up. They give me, so here I'm going to use the fact that 1 over x minus I epsilon, right, the limit of epsilon going to 0, this guy becomes I pi delta of x, right? So I'm going to use that, and then this guy becomes 2 pi I delta of z. Sorry, this is with a minus. This is probably my minus. 2 pi I delta of z minus epsilon k. Oh, yeah, sorry. Okay, then if these are delta functions, we can perform the delta function, and therefore we get that f is equal to zeta over beta sum over k ln of 1 minus zeta e to the minus beta epsilon of k. Oh, sorry, this here is epsilon of k. Epsilon of k. Okay? And this is a very useful expression which we will use as we go along. This is the contribution of, say, free particles or quasi-particles to the free energy. Okay? And zeta is, plus or minus for bosons. And fermions, I'm not going to comment about Green's functions. I also already commented about that a little bit. Yeah, and with that, I'm done with the mathematical introduction, and I want to move to some physics. Questions?
What is epsilon of k?
Epsilon of k. Okay, so I remind you that we assumed that the Hamiltonian, our starting point was that the Hamiltonian H was some d dx, right? Psi bar of x, and then there was epsilon of minus I delta psi of x. So for example, epsilon of minus I delta might be something like minus delta squared over 2m minus mu, for example, which would be particles in a parabolic dispersion.
So this is like that in the momentum space.
This is, yes, exactly.
It's the spectrum of the Hamiltonian. Right?
Yes, it's the spectrum of not of the Hamiltonian, but of the free particles. It's a single particle spectrum. Now we have many, many particles, and each one of them has spectrum. So this is a very useful reference point, because this is like free particles. So when is this expression relevant? So it's of course relevant when you have a gas of free particles, but it's also relevant when you have what we call quasi-particles. So it's very, very common that you have an interacting system, but in its low energy spectrum, you have excitations which behave effectively like free particles. These are called quasi-particles. Okay? And if you want to compute the quasi-particle contribution, and we will use this expression. For example, when we will compute the entropy, the change in entropy across the superconducting transition, following BCS theory, we will find this from this expression here. Okay? Okay, so let me, with the remaining time I have, let's move to the weakly interacting Bose gas and discuss maybe finally some physics. So we're going to use this formalism of actions and integrals over fields to analyze the many problems ahead of us. So I hope it was worthwhile. Also, this was in no way a complete summary of the topic, and you might find it useful to look at some books to understand this more thoroughly. Okay, so what we're going to do now is the weekly interacting Bose-gas. Now the reason is, why are we doing this? Because, as I explained to you, well, I don't know if I explained to you, but you know, superconductors, I think I discussed this in the first lecture. Superconductors are interesting for many reasons, but I think one of the nice points is that they're both fundamentally interesting, like for the theory of, you know, basic science, but also important, you know, for technological and applications and many other things. And even within their theory, there are different fundamental questions you can ask. So one question is, you could ask, how do they form? Another question is, okay, let's say you have a superconductor, how does it behave? What is its properties? And each one of these turns out to be a whole field of its own. Now, it turns out that, you know, chronologically, the first, I think, understanding dramatic, well, there are a few dramatic advances, but I think maybe a very important milestone was when Ginzburg and Landau wrote the Ginzburg-Landau theory and understood that actually superfluids and superconductors are related. They're very similar in their phenomenology. Okay, they have differences, which they, by the way, understood immediately, and where did they come from, but they are related. So they understood that superconductors are somehow a condensate of some charged bosonic liquid, which is very confusing, right? Why is it confusing? Because electrons are fermions, right? So you wouldn't expect naively, you know, and this is something they know. So, for example, if you take helium-3 and cool it down to, say, 1 Kelvin, and you take helium-4 and you cool it down to 1 Kelvin, you will find that helium-4 undergoes a dramatic phase transition and becomes a superfluid. And helium-3 remains, you know, just liquid helium. Okay? And this is what you expect. But somehow, the electronic liquid becomes a bosonic condensate. And this is what we call the macroscopic mechanism. That's not what we're going to talk about now. What we're going to talk about now is how do such superfluids behave. Later on, we'll discuss them. And of course, you know the answer. I'm sure you know the answer. The answer is that basically the electrons first form Cooper pairs. These Cooper pairs behave effectively like bosons, and these bosons condense and give you this superfluid. And by the way, it was later discovered that if you cool down helium-3 enough, okay, then it also becomes superconducting. And what? Superfluid. It's a superfluid. And the superfluid is basically a superfluid of pairs of helium atoms. Okay, so it's the same idea. But that's not what we're doing now. Now we're going to discuss. Okay, so the first thing we're going to do is we're going to do mean field theory. Okay, so this is the most basic thing we can do, the mean field theory. So let's see how it works. So let's start from a Hamiltonian. We have sum over k, k squared over 2m minus mu, a dagger k a k, plus 1/2 this is volume, sum over Q, rho Q, VQ, rho minus Q. Okay, and rho Q is the density of such bosons, sum over K, A dagger K plus Q, A K. So this is some bosonic liquid. The excitations of this bosonic liquid are, it's a parabolic dispersion. So it's bosons, okay, it's bosons that have some parabolic dispersion, okay. Chemical potential is because we're working in the grand canonical ensemble, as mentioned before. And this is the interaction. V of Q is some generic density-density interaction. Okay? Now we're going to study what happens to this boson liquid. And in particular, we're going to take a repulsive interaction. So we assume that V is repulsive. So the way we do this mean field theory. So I didn't show this. I assume that you know this from statistical mechanics. But if you don't have this, what happens if you cool down the temperature of this gas?
Condensation.
What kind of condensation?
Bose-Einstein.
Bose-Einstein condensation. So you have Bose-Einstein condensation, which is a very sick limit. Okay? How do you get Bose-Einstein condensation? You compute, you try to compute the occupation numbers, okay, and chemical potential self-consistently, and what you find is that at a critical temperature, the occupation of the zero state at the bottom of this momentum well, the occupation starts to grow in a way which is extensive. There's an extensive number of particles in this that occupy this zero state. This is what we call Bose-Einstein condensation. But this Bose-Einstein condensate is actually very unphysical because without interactions, these particles don't interact with each other. They are not expected to behave like superfluid, and we'll see that later. That if you would have a liquid like this, you would cool down and you would have condensation, then this condensate, for example, would have no stiffness whatsoever in the sense that it wouldn't flow in a dissipationless manner. So it would be very, very fragile. And this is because the interactions are important, and we will see this. But so the point is that you know that this model has a tendency at a low enough temperature to occupy a macroscopic number in the zero state. And that's exactly what's going to guide us in the mean field theory. We're going to assume, we will assume a condensate, okay, in mean field. So we assume that A of 0, momentum, this is like K equal to 0, okay? This guy is equal to A of K equal to 0 dagger, and this is equal to square root of some N0. N0 is the occupation number in this zero state. This is the number of, okay, a number of bosons in the K equal to 0 state. Then what we do in the spirit of mean field theory is that we're going to look at something which we denote by, so then we denote A of K as A0, as square root of this N0 plus delta A0 if K is equal to 0, and AK if k is not equal to 0. And then we assume that delta A naught squared and AK squared are much, much smaller than N0. Okay, so the idea is that the fluctuation and occupation of these other states is much, much smaller than N0. So we're going to neglect everything in comparison to this N0. So if you do that, what you find is that 1 over two omega, what? Hold on. Yes, 1 over 2 omega sum over k, k prime, and q, v of q, a dagger k plus q, a k, a dagger k prime minus q, a k prime. Okay, so now you could imagine taking each one of these guys to be N0. Now you can convince yourself that it's either taking all of them to be square root of N0 or pairs of 2. And then we have the following terms. So we get rho naught over 2. I'll describe in a moment what rho naught is. And then we have 2 times v of 0, a dagger of k, a k. So imagine that we take the density to occupy the 0 state. That only happens at q equal to 0. So that immediately puts it at q equal to 0. And we have 2 densities. One's this and one's that. So that gives us a factor of 2. Okay? 2. What is this? This is ridiculous. Okay. Then, wait a second. We can also take this and that. Let me see. So we can choose k plus q is equal to 0 and k prime is equal to 0. I see, I made a mistake. Okay, I need to fix the notes. But we can take this like that. Okay? And then, I need to sum here. Hold on. So this is rho naught over 2, sum over k. So you know, this factor of 2 comes from once where I put these two to be 0 and once when I put these two to be 0. But I can also choose that k plus q will be equal to 0 and k prime will be equal to 0. And that implies that k will be minus q, and this is also minus q. Okay, and then what I get, and we can choose this also in 2 ways. So I have 2 v of k, a dagger k, a k, like this. And then the last 2 terms are when I assume that these 2 are 0 or these 2 are 0. Okay, so then I get plus vk, a dagger k, a dagger minus k, plus vk, a k, a minus k. Okay, and here I've used the notation that rho naught is n naught over omega. So if n naught is the number of particles in the 0 state, then rho naught is their density. Okay?
The sigma should be bigger because you sum yourself.
No. But so let's choose any term you want.
Yeah, you chose it, so you all have already summed.
No, but I chose only 2 out of 3. These are two equations, and I have 3 sums. So for example, Q can be a free parameter.
Didn't you say Q to 0?
No, here I set Q to 0 in order to nullify density. But in this term, for example, I assume that these two are 0, and then I'm left with these two.
So you got rid of 2 out of the 3 sums.
Yes, always 2 out of the 3. Because it's basically 2. You need, in each one of these expressions, there were 2. And then there is a third term.
Yonatan, you can explain it again.
So I'm taking this expression, okay? And I am okay. So imagine that instead of this guy here, I write this guy as let me write this as A0 plus, let me call this for a moment B of K plus Q. Okay, and this is A0 delta K plus Q 0. Okay?
Okay.
And then this term is the 0, and this describes the fluctuations around it. So I plug this in here, plug this in here, plug this in here, and plug this in here. Okay? Now this guy, I remind you, is square root of n. No. So this guy is big. Much, much bigger than these guys. So I'm going to take only quadratic order in B everywhere. But then you have different possible combinations depending on this delta function. Will give you these different terms. Okay?
Why does it not really equal?
Well, because you have quartic terms where B multiplies B multiplies B multiplies B. But we assume their contribution to be small. This is mean field. This is what mean field means.
In advanced quantum mechanics, we said that this kind of operators are nice and this kind are not very nice to deal with.
Again, what? These guys?
Yeah.
You said that they're not nice?
Where you have twice dagger or twice no dagger.
Yes.
So there are.
Which, that's what you said, that they're not nice, but did you take care of them or not?
We said we categorized the operators to one body, two body, n body, and we said, I don't remember how we call it.
No, you're right that there is something. By the way, this is kind of the point. Okay? We will talk about this later, but the point is that when we assume a condensate, what are we doing here? We're basically assuming that there is some mean field condensate. And this condensate, okay, it has, there are particles in the condensate, and these particles can be injected out of the zero momentum state into the finite momentum states and back. So this process here, this term here, represents a situation where you have a pair ejected from zero momentum to finite momentum. Okay? And this is the opposite way around, where you have a pair at kn minus k, which go into zero. And now you can also see why you can only have these quadratic terms, because you need to conserve momentum. So if you have, at zero momentum, you have a condensate, you cannot eject a single particle into finite momentum because it has zero momentum. But it can eject a pair like this. Okay? So, and this is all a matter of this assumption. We substitute an operator with a number. Okay? And we assume that this number, once we did that, we yeah, that basically leads to this kind of bath of particles that can emerge or disappear into this vacuum.
And the fact that you eject or catch them in pairs, does it mean that also when they are not in the condensation, they are still entangled?
Again. Whoa. Entangled.
No?
Yes, okay. If you want to talk about entanglement, that requires talking about wave functions. You're of course right that this pair will be entangled in some sense, but I don't want to discuss that because it's. But what was the question?
They are entangled in the condensation, right? And
They are entangled in the condensation.
And then
That's true, but that's not trivial
inject
to
them
see them.
in pairs.
Yes.
So they
No,
eject
but you have to understand that at least according. First of all, this formalism is not very good to discuss their entanglement. And second, it is of course correct that they are entangled in the condensation. But the pair, they are ejected in pairs because of conservation of momentum. By the way, you can eject more, but we're not. Principle, this Hamiltonian would also allow process like higher order processes. Of course, Okay, let's see where we go with this. So now. Okay, now, Okay, so now the next step, what we're going to do is we're going to absorb this and that into the chemical potential of these particles because it's proportional to density. Okay, so I write H mean field now is equal to a sum over k, k squared over 2m minus mu of k now, which I'll write in a moment, a dagger k, a k, plus sum over k not equal to 0. Oh, by the way, yeah, this is here is k not equal to 0. It's not equal to 0 for a very simple reason, because the k equal to 0 part contributes, the condensate. And then we have rho naught vk over 2 a dagger k, a dagger minus k, plus a k, a minus k. And this whole thing has plus rho naught squared omega v naught over 2. And mu of k is let me even observe this here. Show you in a moment. So I write mu minus rho naught v naught minus rho naught over 2 times vk plus v of minus k. Okay, not that it matters that much because the interaction is of course symmetric. So you know what, let me even erase this. I don't need to complicate you with the details. So rho naught vk. Okay. Questions?
there where you said k not equal to 0, k goes both to infinity and minus infinity?
It's all the case.
So
I didn't even specify what they are. It's a
directions.
parabolic dispersion, so it can be an n-dimensional liquid. I don't care. Okay? Okay, so now this is the Hamiltonian we need to solve. And do you know how to solve this?
Yes, of course.
And the answer is?
No.
Some of you
No.
saw it, no? What's the name of the transformation? No?
Legendre.
Bogolyubov. We do a Bogolyubov transformation. Okay? So the Bogolyubov transformation is, okay, so we defined some new operator alpha of k, okay, which is u of k, ak, plus vk, a dagger of minus k, okay? And we want, in order for this transformation to be valid, what do I need to make sure that happens? Or what needs to be conserved?
Momentum.
Mm-mm. No.
No.
Number
Energy.
of particles.
What?
Number of particles.
That's related, but how do I make sure? What? So, what are these guys?
Like annihilation and destruction.
Yes. Okay. So, and what do I want this guy to be? An annihilation operator, right? So if this guy is an annihilation operator, I need to make sure that what? What makes it an annihilation operator?
That it's diagonalizes the coordinates.
On the vacuum you get 0.
And it's
That's also true. But the algebra, I need to make sure that the algebra is conserved. Okay, so I need to make sure that a alpha of k, alpha dagger of k, is equal to 1. Right? This is what I need to make sure. Okay, now what is alpha of k, alpha of dagger of k? That's uk ak plus vk a dagger of minus k. And here we have uk ak dagger. I assume that u and v are real. Okay, you know what? Let's not assume that. Let's be more generic. U plus v of k star a of minus k. Okay? Now, this guy does not commute with this guy, and this guy does not commute with this guy. So what we get is, now this with that gives me 1. This with that gives me what?
Which one?
This with that gives me 1. Like A,
Right.
A of k, A of dagger of k is 1. So what is A of dagger of minus k, A of minus k, for example? Minus 1. Good. So what I get here is uk squared minus vk squared. Okay, so if I want to conserve the commutation relation, I need to choose functions that obey this condition, and this motivates us to use uk is equal to e to the I phi cosinus hyperbolic of some angle theta of k, and v of k is equal to I phi sine hyperbolic of theta of k. Okay? And yeah, and then the transformation matrix, so if I want to transform from alpha of k, alpha dagger of minus k, okay, then what do I have here? I'm going to have something like
both minus k and dagger?
You know what? Let me actually, I have more freedom than that. Let me write it like this. I'll explain in a moment why, because this can have a relative phase compared to that one. Okay? Then in this case I have cosinus hyperbolic theta of k e to the I phi sine hyperbolic of theta of minus k, and then this would be e to the minus I phi sine hyperbolic of theta of minus k, and this would be cos hyperbolic of theta of minus k, acting on a of k, a dagger of minus k. So what I want to comment is that this transformation matrix is non-Hermitian. Okay? It's what we call a canonical transformation, in the sense that it conserves the commutation relation. But it's not, sorry, did I say non-Hermitian? I meant non-unitary. It's not a unitary transformation. For fermions, it is unitary. Okay? Because for fermions, when we switch the two, it doesn't matter. It's an anti-commutation relation. And then this becomes a plus, and you choose cosine and sine functions, and everything's A-OK. But here it's not a transformation matrix, and that's a problem. I don't know if it's a problem, but that's a property of the Bogoliubov transformation. Okay, then what we do is we choose these functions, u of k and v of k, so choose u of k and v of k such that alpha of p, let's call it alpha of p, and h mean field, h mean field, will be equal to EP alpha p. Okay? Why do we do this? Because this implies that H is equal to a sum over K, EK, alpha dagger K, alpha K, plus some constant, which I will denote as the ground state energy. This K is, by the way, not equal to 0. This is only the not equal to 0 part. Okay? And you can choose U of K and V of K that obey this relation. You'll find that U of K is equal to the sum of K squared over 2m minus mu K divided by 2ek plus 1/2, and V of K is equal to the square root of K squared over 2m minus mu of K minus 1/2 divided by 2ek, and then ek is equal to the square root of K squared over 2m minus mu of K minus rho naught V of K squared. Okay? And the ground state energy that we get in this case is omega times 1/2 rho naught squared V naught minus mu rho naught minus sum over k not equal to 0, 1/2 k squared over 2m minus mu k minus ek. Okay, so this is basically the solution. Now what does this solution give us? It implies that our Hamiltonian that's written here, this is by the way the mean field Hamiltonian, mean field. So this mean field Hamiltonian is described by these quasi-particles. These are the excitations. Each one of these excitations, this is called the Bogolyubov quasi-particle, or a Bogolyubov excitation. Each one of these excitations carries an energy Ek. The ground state, at 0 temperature, you have no excitations. The energy of the system is going to be E ground state. Okay, this is what this describes. This is what we obtained using this transformation. Now, let's study this model a little bit. Okay? Now, what we did up to now is we just assumed that there is some fraction, some extensive amount of particles that condensed in the zero momentum state. But in order to make the mean field theory complete, what we do is we want to determine this condensate fraction self-consistent. Okay? In particular, we want to ask what is the minimum energy or minimum free energy solution. Okay, so you could ask, given a specific temperature, what minimizes the free energy, and you find that actually the fraction, this condensate fraction rho naught, depends on temperature. Okay, is that clear? So what we want to do that's not, So we can basically do, we can do this in two ways. One of them is self-consistency, and the other one is one moment. Let's not. Okay, so in the next step, to find rho naught and mu that obey the constraint on total particle number and minimize the free energy. Okay, so in principle, what we really need to do is we need to compute d to d rho naught of h minus t s, where s is the entropy, And we need to make sure that the sum over k not equal to 0. A dagger k, a k plus n naught is equal to n. Okay, so this is conservation of total particle number, and this is minimizing the free energy. So,
but if we are non-canonical, shouldn't there be minus mu n?
you're asking about the
what you are.
no, H contains the minus mu n, okay? But yeah, H contains the, but all I'm saying is that the energy itself, okay, is not enough to minimize. You need to take into account entropy. Okay, but there is an equivalent this thing. It turns out that this by the way, I didn't mention this should be equal to 0. We're minimizing. Okay, there's an equivalent formulation of this. One can show that you can compute I guess AK, A minus K, I think is equal to N0. So you can show that, I need to check, I don't remember actually now if this is enough, but I don't want to get too much into the details, and it appears in the literature. It's not something super sophisticated, but basically what we want to do is minimize the free energy while maintaining this constraint. And when you do that, so I'm sorry I'm a bit descriptive that I'm hand waving through this. So what we're going to do is we're going to assume a few simplifications. Okay, so to simplify, we assume that V of Q is equal to V, which means contact interaction. Okay? So in that case, okay, and in this case, we expand the the ground state. The ground state, we expand E ground state to let's expand 1/2 k squared over 2m minus mu k minus ek to lowest order in k. So what we find is that that 1/2 k squared over 2m minus mu plus 2 rho naught v minus square root of k squared over 2m minus mu plus 2 rho naught v. This whole thing is squared minus rho naught v squared. So what I'm doing now is I want to expand this, okay, in k. Okay, and what you'll find is that this guy goes like rho naught v squared k over 2 square root of 2m. Okay? Therefore, to lowest order in V, the ground state energy is equal to rho naught V minus mu plus O of V squared. Okay, so this in the limit where we take a contact interaction and we look at the lowest, at the weakly interacting Bose gas, meaning that V is small. In this case, the ground state energy becomes this. Okay? Yeah, let's not erase this result. I'll leave it here. How much time do I have? 3 minutes. Okay, quickly, let me just summarize the result. What you find then is that dE ground state, d rho naught, okay? Sorry, this is like this, okay, and then dE rho ground state, this is rho naught squared V over 2 minus mu rho naught, okay. And then this guy is equal to rho naught V minus mu. And if we equate this to 0, we get that mu is equal to rho naught V. Okay? This is one solution. Now plug this in the dispersion E of k. Okay, look at E of k here. So mu, I remind you that mu, in this case, this becomes k squared over 2m minus mu plus, what do we have here? Plus 2 times rho naught v minus rho naught v squared, and this whole thing is squared. Okay, so if mu is equal to rho naught v, like it's written over there, then this and this cancel, and we have k squared plus rho naught v, and then minus rho naught v outside. So what we get is ek is equal to square root of so let me open this up. So I have k to the 4th 4m squared. That's one term. Then this guy gives me plus 2 times rho naught v k squared over 2m. And then this guy gives me a plus rho naught v squared. And then the whole thing is minus rho naught v squared. So this and this cancel, okay? And then we obtain a very important result, which is basically a k over square root of 2m times...
Why is not 4 row 0?
Shouldn't it be 1?
4 rows, what?
In the,
Here, this?
yeah, if you square it.
No, because mu is rho naught v,
Oh,
so this... That's the whole point. That at the solution, okay, let me get to the point. So the point is that then this becomes 2 rho naught v plus k squared over 2m. Okay, so what we found is that the dispersion of these quasi-particles, ek, as a function of k, looks something like this. Okay, so here it's basically parabolic, and here it's linear. Where the slope here is, you know, it's like square root of rho naught v over m. This is like the velocity. This is the velocity of these quasi-particles. Now, the point is this. Here, I needed to do all this hand waving and assume that the interaction is weak, so I can neglect, and you know, I plug this mu, and it seemed like magic that they exactly cancel each other, like some very delicate condition, and that's exactly what you need to get a gapless dispersion here. And this is an important lesson that shows us why working with a quantum field theory is much better than working in a Hamiltonian or doing mean field theory. Because you'll see in next lecture, you'll see that this wasn't accidental. Actually, this must happen all the time. It's because of symmetry. Okay, so these modes are what we call a Goldstone mode. Okay, and they must be gapless by symmetry. But in order to get to the mean field theory, we need to do all this juggling and all this stuff. This is very bad. This is one comment. The second comment, these Bogolyubov excitations are basically density excitations in the superfluid. And I just want to comment that if this is like the weakly interacting, this is weakly interacting, okay? But if you have a strongly interacting liquid, basically the velocity is also linear, but then you have what they call a Roton minimum. Okay, this is what they call Roton. Okay, and that's important for all sorts of other stuff that we will discuss later. That's important to know. But to get this line from the mean field theory is very difficult, because then you can imagine that I can't neglect anything. And I'm going to work, like if you do that calculation, it's very hard to make sure that the, first of all, then this kind of trick doesn't work, because I need to remember that I'm working with a free energy and not minimizing just the ground state, because there's temperature and entropy and all that. And another issue which complicates things is I need to make sure that the dispersion remains gapless as it should. It becomes very delicate. And that's like a mess. But we'll see in the field theory that everything becomes much simpler. Okay? So yeah, next time. This is the Bose gas. And yeah. Yeah, actually, sorry. Let me correct one thing. So this solution that I did is correct at 0 temperature. Okay? So all the comments I made about the entropy, that's only if you want to calculate it at the finite temperature. So that's also a complication which, but even if you want to do it at 0 temperature with this, it's complicated because you need to take all the orders into account consistently, such that you get a gapless dispersion, and we'll learn in the next lecture why. And maybe one last comment is that if you would do it at finite temperature, then you would get something like this, basically. So this is the condensate fraction as a function of temperature. This is the condensation temperature. So Tc, let's call it. And the chemical potential is basically negative. Yeah, it's basically negative. It might change slope, and then it goes up together with, so it's like mu, and the Tc is like the order parameter is basically like 0 above the condensation temperature. Okay. Okay. See you next week. And regarding the question whether we'll have the course, so I decided we will, of course, continue this course, and I don't think we'll have an exam. I think we'll just have like I'll give you some sort of exercise to study a well-known paper in superconductivity and write some sort of report, or maybe do a presentation. We'll see. We'll arrange it. Okay? Sounds good? No?
So also,
What?
that's the main show line.
לא, זה לא אמר.
שניים בקרחתי לך שכל לך הביתה?
לא, אני חושב שאני לא כל כך.
יש לי כמה שאלות. לא יודע כמה זמן יש לך? אתה ממהר?
אני קצת ממהר, כי יש לי פגישה.
רוצה במייל?
אתה
כן, עדיף במייל או תקפוץ אליי ביום אחר, כי יש לי פגישה ב-11:45.
אוקיי, אז אני ארשום לך במייל, ואם אתה חושב שצריך להיפגש על זה, אז